Hello everyone, and welcome to today's lecture on circuit sources. Today we're going to cover the differences between real and ideal sources, as well as how to handle circuits with multiple sources. So first, sources. There are two kinds: a voltage source, which provides voltage, and a current source, which provides current. And we can have independent or dependent sources. Independent sources always strive to provide whatever value it is set at. For instance, a voltage set to 5 volts will always provide 5 volts across its terminals, regardless of what else is happening with the circuit. And a 3 amp source will always maintain 3 amps across its terminals, regardless of what else is happening in the circuit. Dependent sources, however, adjust their values based on some input. Usually this is an input voltage or an input current. More on that in a bit. First, we're going to cover the differences between real and ideal sources. So an ideal voltage source will adjust the current it sends out in order to keep voltage across its terminals constant. And this is different from the ideal current source, which simply sends out and maintains that current across its terminals regardless of what else is happening. So the first big difference between the real and ideal sources is the limitations of the source device. Realistically, a voltage source can only send out so much current before it overheats or begins to break down, if there is even that much current available to it. And a current source has to keep fighting against load resistances, which may lower current or increase voltage across the device beyond the ability to keep up with it or to keep from melting. An additional difference between real and ideal sources is that real sources have some kind of internal resistance. In the case of the voltage source, a real voltage source is modeled as a resistor in series with an ideal source. And in the case of real current, the model is a resistor in parallel with an ideal current source. So what are the implications of this? The typical way to analyze these is through the IV characteristics curves, or the current voltage characteristic curve, where we simply plot the device's response on the current and voltage axis, or the current voltage plane. For an ideal voltage source, the top left, regardless of the required current, voltage is always constant. However, we do see two distinct regimes. The first and most typical case is for positive current, or current flowing away from the source. In this regime, the source is providing power to the circuit. If, however, current is flowing to the source, in order to maintain the appropriate voltage difference, the source has to absorb power from the circuit. You can think of these similar to charging or discharging your phone battery. When discharging, your battery is powering your phone. You're able to look at Facebook or whatever. And then when charging your battery, the battery is taking power from your charging port that you're plugged into. And those are the two regimes, absorbing power or delivering power. For an ideal current source, top right, regardless of the voltage across the leads of the source, we have a constant current. And just like the voltage source, there are two regimes. In the case of positive voltage, power is delivered. In the case of negative voltage, power is absorbed. In the real case, things are slightly different for both. We're going to model these as load-less versions of the sources, so we're not attached to any circuit. It's just the internal resistances of our sources. For a real voltage source, bottom left, the actual voltage output is lessened by the voltage lost across the resistor. And this gives a negative slope to our IV relationship, where our slope is the value of the resistor. And the difference between the ideal output and the real output is equal times the current having to be sent out from the voltage source across the resistor. So I out times the internal resistor value is what's removed from our ideal source. Similarly, the current source's output is lessened by current lost to an internal loop created by the internal resistance. So if we send out current, some of it's going to want to go through the loop back to the negative terminal of our current source via our internal resistor. And this is also going to cause some kind of voltage difference between the two. But most importantly, because the current source is supposed to provide constant current, it loses current through that loop. And the amount of current lost is equal to the voltage across those two resistors over the resistor value. Notice that we recover our ideal values when resistor value is 0, our internal resistor value is 0 for a voltage source, and our internal resistor value is infinity for a current source. This makes a lot of sense because if we have a 0 ohm resistor for our real voltage source, you're not going to lose any voltage going across it. R is equal to 0, voltage across is 0. For the current source, if you have an infinite resistance, you're not able to push electrons through there, so we don't have a closed loop. It's a gap instead. So we're not going to lose any of our current to that internal resistance. All right, now we're going to talk about the dependent sources. So dependent sources are controlled by the rest of the circuit. The diagram notation is a diamond with the plus minus denoting the voltage source and an arrow denoting the current source. And it should surprise nobody to learn that the direction of the arrow indicates direction of flow, and the plus side is the high voltage. And the biggest difference between dependent and independent sources is dependent sources adjust output proportionally to some input voltage or current. Depending on whether the source is controlled by voltage or current, we have a scaling factor that we multiply our input by to get our output. A dependent voltage source on the top left that is voltage controlled, the output voltage provided by our source now is equal to mu times the input voltage across. So in this case, mu is a unitless scaling factor because when you solve for it, you just have V out over Vn. And it's just going to scale up or multiply our input value by some amount. If it's a current controlled voltage source on the bottom left, we have a scaling factor of rho, which is in units of ohms. So it has to have ohms because we have a controlled current and our output is controlled by the current. So V out over IN equals rho, which must be in units of ohms. However, it's important to notice that this is not an actual resistance, but simply a multiplying factor which happens to share the same units. And this is going to matter when converting between real and ideal dependent voltage sources, because you don't want to accidentally include this as part of the internal resistance. On the right side, a current source controlled by voltage is scaled by a factor often denoted by alpha, which has units of Siemens or inverse ohms. And in terms of Ohm's law, this current is equal to voltage over ohms, which inverses the unit. But once again, not an actual resistance, just a scaling factor with similar units. On the bottom right, if our current output is controlled by a current input, the scaling factor is beta, which does not have units in this case, just a simple unitless scaling factor. As a rule, the scaling factor multiplies the input to produce output. We can also include a shift up or down by including independent sources, but we would usually handle these separately from each other to make our math more simple. And now for how to combine some sources. Voltage sources simply add when we have them in series. The only tricky part is pay attention to direction of output and switch signs appropriately. If the plus signs are both facing each other, the total voltage is the difference. If they're both facing in the same direction, the total out is the sum. When they're in parallel, however, it's a little tricky. We are only allowed to place voltage sources in parallel if they are equal to each other. Remember that by definition, components in parallel have the same voltage, and two voltage sources in parallel without the same voltage violate this rule, and we can't do it. This gets a little fuzzy if there are more components in the branch, like if there's a series of resistors between one or the other. Then we might be able to work it out, but it really depends on the rest of the circuit. So just in general, it won't happen. As for current sources, they behave sort of opposite. In series, we can only place two sources if they have the same current output, because each source is trying to ensure that the branch they are on has a specific current, and two sources competing with each other won't work. They'll never reach an equilibrium. But in parallel, our sources add up. Because they're on separate branches of our circuit, there's no conflict. We just have to remember to pay attention to the flow and then add the two sources together or find the difference. So the rules aren't that complicated. The only thing to do is pay attention to if we're in series or parallel and which direction things are going, and remembering our rules for parallel and series, where series must have the same current and parallel must have the same voltage. So I'm going to start showing you guys circuits and having you solve for circuits that have multiple sources. So I'm going to show you an example of that so you know how to get through it. So we're going to do an example problem with 3 sources, 2 of which are voltage and 1 current. And we're going to want the current through resistor 3. The general method or algorithm involves taking advantage of superposition and solving for each source separately and then adding. And remember, we can use superposition because circuits are linear. So the total result is the sum of all of the individual small bits. And right now we have 3 bits contributing to what's going to happen across resistor 3. Okay? So, rules of thumb. When treating one source, you turn the others off. And this makes voltage sources become a short because remember, an ideal voltage source has an internal resistance of 0, and it makes current sources become a break because ideal current sources have an internal resistance of infinity. So let's do V1 first. When we do that, we discover that we have a short in our circuit before we even get to resistors 2 and 3. So if we have a short right there, why would an electron ever choose to go through resistors 2 and 3 if they can just go through that straight wire and just go right back to where they want to go? So we can just stop there. Resistor 3 has no contribution from voltage source 1. So we're going to remember that. Second voltage source. Once we turn off our other sources, we find that this is just a simple parallel circuit. In this diagram, it might not look exactly parallel, but if you were to rearrange the shape of this drawing, you would find that there are 2 branches in our circuit. So this one's pretty easy to solve as well. Voltage source 2 is providing 2 volts across each parallel branch. We only care about the branch really that has resistor 3 in it. So it's dropping 2 volts across a branch that has a total of 11 ohms in it. And remember that we don't need to solve specifically for resistor 3, just for the current through that branch, because all the current in that branch is going to be equal to each other. So we have 2 volts over 11 amps is 0.1818 amps. Simple. Now for the third source, or the current source. So after turning off our other 2 sources, we find that we once again have a short in our circuit, but this time it shorts out resistor 1 because now the current flowing down either side of our nodes are going to go through resistors 2 and 3, but not hit 1, because why would they ever go through a resistor when they have that nice simple wire to go through? So this is once again a simple parallel circuit, and we can just use the current divider formula, if you remember that, to find the current through our branches. And remember, the current divider formula is the current through a particular branch is equal to the total current of our circuit times the total resistance over the resistance of our branch we're looking at, which in this case, total resistance is 2.1818, because remember, things in parallel, you have to add together using the inversing formula thing, which always turns out to be less than any individual resistor on any other branches. So that's good, that makes sense. And then the resistor we care about is on a branch that has a total of 8 ohms on it. So we have 2.1818 over 8 times 2 gives us a total of 0.5454 amps. So that's all of our sources that we solve for. Source 1 contributes no amperage to resistor 3. Source 2 contributes 0.1818 amps, and source 3 contributes 0.5454 amps. So that means that the total current across our third resistor should be the sum of all 3 of those. So 0 plus 0.545 plus 0.182 gives us 0.727. And we're done. If you aren't sure about this, I encourage you to go to Multisim and try the circuit out for yourself and check the result. So one important thing to note is that this kind of circuit analysis gives the steady state response and does not take into account transient inputs. So for that kind of thing, we're going to start turning to differential equations and Laplace transforms to solve those circuits and the transient responses. However, if we're just looking for the steady state response or the long-term behavior with a constant input, this is a pretty simple way to start looking for that kind of resolution. All right, and that's all for this one. Thank you for watching.